compact stars in scalar tensor theories with a single well potential exhibit distinct properties, particularly in the context of F-R theory. The authors of this study investigate the hydrostatic equilibrium structure of neutron stars using a polytropic equation of state in the Jordan frame, with a simple potential V, phi, equals off squared, 2 in the Einstein frame. Here, phi represents the scalar field, and omega is a constant. Modified gravity theories, such as F-R theories, can significantly alter the macroscopic properties of compact stars, deviating from general relativistic predictions. This is because F-R theories can be cast as scalar tensor theories, where the Lagrangian is written as the standard Einstein-Hilbert Lagrangian with respect to the new metric, plus an extra scalar field subject to a given potential. The motivation for introducing modifications to general relativity stems from theoretical and observational aspects, including the need to explain primordial inflationary scenarios, the current accelerated expansion of the universe, and the possibility of extra-massive neutron stars with non-exotic equations of state. The authors aim to test the viability of F-R gravity theories in the context of spherically symmetric relativistic stars, which provide a unique testing environment due to the large range of values for the Ricci scalar. By adopting an alternative approach, starting from the Einstein frame with a simple potential, the authors investigate the mass-radius relations, proper mass, and binding energy of neutron stars in the Jordan frame. The results reveal that the maximum mass values increase substantially as omega decreases, while the radius and mass decrease in the low central density region as one moves away from the pure GR scenario. A notable feature emerges when the binding energy is plotted as a function of the proper mass, where a cusp is formed, indicating the appearance of instability. The central density value where the binding energy is a minimum corresponds precisely to dm d rho jc equals 0 on the m rho jc curve. This suggests that the stability of neutron stars is significantly affected by the scalar tensor theory, with implications for our understanding of compact objects in modified gravity theories. This study explores the relativistic structure of neutron stars within scalar tensor theories, concentrating on a specific coupling function and a single well potential for the scalar field in the Einstein frame. A key distinction between this research and previous literature lies in its interpretation of these theories as F-R gravity in the Jordan frame, providing a stronger motivation for the choice of the function F-R. The paper begins by defining the Einstein frame action and the corresponding functions F-R and R in the Jordan frame. It then presents the modified TOV equations and defines the gravitational binding energy for polytropic compact stars. The numerical results are discussed in terms of the mass-radius diagram, the function F-R, and the binding energy. The approach taken in this study is distinct from previous works in the literature, both in stellar and cosmological contexts, and yields different results, albeit numerically similar to those of general relativity. The paper's findings contribute to the ongoing research on scalarization and its manifestation in compact objects, offering insights into the potential implications of scalar tensor theories for our understanding of neutron stars and their behavior. The modified gravity Lagrangian in the Jordan frame, JF, is defined as L_J equals sqrt G_J F R_J, where R_J is the Ricci scalar. A Legendre transformation is performed to replace the independent variable R with phi equiv F equiv dF doctor, resulting in the Lagrangian L_J equals sqrt G_J left phi R phi W phi right, where W phi equiv phi R phi F R phi. This transformation allows for the introduction of a new scalar field, phi, which is related to the original function, f(r). A conformal transformation is then applied to transform the action to the Einstein frame, EF, where g_mu nu caret e equals phi g_mu nu caret j. The action becomes s equals frac 1 2 kappa int d caret 4x sqrt g_e left r_e 2 grams _e caret mu nu partial underscore mu phi partial underscore nu phi v phi right plus s underscore m left phi caret 1 g underscore mu nu caret e psi right, where v phi equals frac 1 2 omega phi a squared is the potential for the scalar field phi, and s underscore m is the action for matter radiation fields denoted by psi. The corresponding f r in the JF is obtained using a previously established procedure and is defined as f phi equals e caret 4 phi sqrt 3 left 2 volts phi plus sqrt 3 frac dv phi d phi right and r phi equals e caret 2 phi sqrt 3 left 4 volts phi plus sqrt 3 frac dv phi d phi right. These expressions are plotted in figure 1, showing a 3-branch structure for f r, with f r greater than 0 for all r, but f r less than 0 in the lower branch, indicating instability. The paper notes that the bottom of the potential v phi, i.e. phi equals a, corresponds to f equals 0 equals r, and that the full range of r around this final value grows exponentially with phi. Assuming a equals 0 for simplicity, the authors obtain the field equations in the Einstein frame by varying the action with respect to the metric tensor g underscore mu nu caret e and the scalar field phi. In the context of scalar tensor theories of gravity, the Tolman-Oppenheimer-Volkoff (TOV) equations are modified to describe the structure of compact stars. The Einstein and Jordan frames are introduced, related through a conformal transformation that depends on a scalar field. The field equations in the Einstein frame are derived, including the Einstein equation and the Klein-Gordon equation for the scalar field, as well as the conservation law for the energy-momentum tensor. Spherically symmetric and static metrics are considered in both frames, providing relations between the radial coordinates, lapse functions, and radial metric components. The energy-momentum tensor of an isotropic perfect fluid in the Einstein frame is described, along with its relation to the Jordan frame. This leads to expressions for the energy density, pressure, and for velocity in the Einstein frame. In the hydrostatic equilibrium state, the modified TOV equations are derived from the field equations and conservation law, using the energy-momentum tensor components. These equations describe the structure of a compact star in scalar tensor theories, accounting for the effects of the scalar field on the gravitational field and fluid properties. The importance of these equations lies in their potential to understand the behavior of compact stars in such theories and their implications for astrophysical observations. The modified TOV equations provide a framework for studying the internal structure of compact stars, including neutron stars and white dwarfs, in the context of scalar tensor theories. By incorporating the effects of the scalar field, these equations offer a more comprehensive understanding of the complex interplay between gravity, matter, and scalar fields in extreme astrophysical environments. In the context of modified gravity theories, the stellar structure equations in the Einstein frame describe the behavior of compact stars. These equations, derived from the modified Tolman-Oppenheimer-Volkoff (TOV) equations, take into account the effects of the scalar field on the stellar structure. Specifically, equations 22a, 22d describe the energy density, pressure, and metric functions of the star. The relations for energy density and pressure in both the Jordan and Einstein frames are discussed. The equation of state in the Jordan frame can be written in terms of Einstein frame quantities, taking the form of a polytropic equation of state, Pj equals kjrgj, where gamma is the polytropic index. This equation is then transformed into the Einstein frame, yielding P equals krge, where k is a function of the scalar field phi, r. To solve the modified TOV equations numerically, the initial values for the energy density, metric functions, and scalar field are specified, and the asymptotic flatness requirement is imposed. The energy density and pressure of the scalar field are identified, expressed in terms of the scalar field and its derivatives. The gravitational binding energy, a measure of the stability of compact stars, is also defined. The numerical solution of the modified TOV equations involves integrating the equations from the center to the surface of the star. The physical radius and total gravitational mass of the star are calculated, with the polytropic index gamma and the coefficient kj fixed to specific values. The effects of the scalar field on the stellar structure and stability will be investigated in the following sections, using rewritten forms of the modified TOV equations, such as equations 30a and 30b, to identify the energy density and pressure of the scalar field. Scalar-tensor theories of gravity, which postulate the existence of a scalar field, have been explored in the context of neutron star configurations. To model the neutron star structure, the modified Tolman-Oppenheimer-Volkoff (TOV) equations are employed, incorporating a scalar field with mass m phi and potential v phi. Numerical solutions of these equations are obtained for various central densities and scalar field masses, providing insight into mass-radius diagrams and the scalar field's behavior at the star's center. The results indicate that decreasing the scalar field mass leads to significant increases in maximum mass values in the mass-radius diagram. Furthermore, the star's radius decreases in the low-mass region due to the scalar field's presence, although this trend reverses at higher central densities. The central scalar field decreases with increasing scalar field mass before reaching the maximum mass, consistent with the mass-radius relation. In the limiting case where the scalar field mass approaches infinity, the general relativity (GR) solution is recovered, with the scalar field tending to zero and the potential v phi approaching zero. This study underscores the importance of considering scalar-tensor theories in neutron star physics, as they can significantly alter the predicted mass and radius of these compact objects. This research contributes to our understanding of how scalar fields influence neutron star structure and properties, potentially shedding light on the nature of dark matter and dark energy in the universe. The mass-radius diagram for compact stars with polytropic equations of state is presented, showcasing the impact of varying the free parameter omega on maximum mass values. The decrease in omega yields larger maximum mass values compared to the general relativistic counterpart. The diagram includes the central compact object within the supernova remnant Hess J173137, with a mass of 0.77 plus 0.20 minus 0.17 m circled dot operator and radius of 10.4 plus 0.86 minus 0.78 kilometers. The radius and mass of these equilibrium configurations are examined as functions of central energy density, revealing a reversal in behavior beyond a certain value of ρc. The scalar field at the stellar center is plotted against the asymptotic mass, with values chosen to satisfy the asymptotic flatness requirement. The gravitational binding energy is analyzed as a function of proper mass and central density, exhibiting a cusp in the high mass region for the adopted massive scalar tensor theory. The minima in each curve correspond to a certain central density value where the mass is maximum, highlighting the importance of binding energy in constructing stable equilibrium configurations. These results are consistent with the standard stability criterion in Einstein gravity, dm, d rho c equals 0, and demonstrate the significance of polytropic equations of state in understanding compact star structure within the framework of scalar tensor theories. The estimated mass and radius of the remnant Hess J173137 are consistent with previous results obtained using massive scalar tensor theories and a polytropic EOS. In the context of massive scalar tensor theories with a simple Diliton potential, the authors delve into the properties of compact stars. Figure 6 illustrates the gravitational binding energy as a function of the proper mass and central mass density for the compact stars depicted in Figure 3. The emergence of a cusp in the binding energy curve corresponds to the central densities where dm, d rho jc equals 0 on the m, rho jc curves, as observed in the bottom plot of Figure 4. The authors note that solutions crossing the three branches in Figure 1 are not feasible, as even a small layer in the unstable region, f, less than 0, would jeopardize the entire star. This instability differs from that in general relativity, gr. They also highlight that, even in the standard unstable branch of the mass-radius plot, f greater than 0, which does not prevent the existence of non-trivial solutions belonging solely to the first branch. Phi is defined as f much less than 1 in Figure 1. In this case, RJSURRRESURR, which would likely lead to unusually low central densities. The authors suggest that this would result in a larger effective Newton's constant. Geffen is defined as Gn, phi, inside and near the star. They propose that finding such solutions would require a fine-grid search in the parameter space, considering the variation of an extra parameter. A shift in the ground state of phi to allow for a corresponding large variation on r. The authors also mention a qualitative change in f, r, not investigated in this paper. The unstable branch, where f less than 0, is known to be absent if one adds an ad hoc lambda to equation 5, whose value is above a critical number. However, reasonable values of lambda are not expected to have a measurable impact on the star's structure, mass, or radius. For the adopted values of omega, the authors find that the maximum mass on the ρjc curve increases with the decrease of the mass of the scalar field m phi, while the radius and mass decrease in the low central density branch. A cusp is formed when the gravitational binding energy is plotted as a function of the proper mass, indicating stellar instability within the framework of massive scalar tensor theories with a simple Diliton potential. Gravitational physics has made significant strides in understanding celestial bodies as sources of gravitational waves, crucial for probing the strong-field regime of general relativity and testing alternative theories of gravity. Neutron stars and black holes are paramount in this context, and researchers have employed theoretical models to describe their behavior. Scalar tensor theories, in particular, have garnered attention, as they introduce an additional scalar field to the gravitational sector, leading to the emission of scalar waves. The presence of this scalar field can impact the orbital decay rate of binary systems, providing a means to test scalar tensor theories against observations. Notably, neutron stars in these theories can exhibit spontaneous scalarization, where the star develops a non-vanishing scalar field even in the absence of an external scalar field. This phenomenon distinguishes neutron stars in scalar tensor theories from their general relativistic counterparts. The implications of scalar tensor theories on gravitational wave signals emitted by neutron stars and black holes are profound. Scalar waves emitted by these sources can be used to constrain the parameters of the theory, while the orbital decay rate of binary systems can be affected by the presence of a scalar field. These effects provide a unique opportunity to test scalar tensor theories using gravitational wave observations. The properties of neutron stars and black holes in scalar tensor theories deviate significantly from their general relativistic counterparts. Specifically, neutron stars in scalar tensor theories can exhibit distinct features, such as spontaneous scalarization, which can be used to constrain the parameters of the theory. The orbital decay rate of binary systems, in turn, can be affected by the presence of a scalar field, providing an additional means to test scalar tensor theories. Future research directions include using gravitational wave observations to further test scalar tensor theories and developing more sophisticated models to describe the behavior of neutron stars and black holes in these theories. By exploring these avenues, researchers can gain a deeper understanding of the strong field regime of gravity and the role of scalar tensor theories in describing the behavior of celestial bodies.